Good morning. This is Sharanya and we discuss about the topic today eigenvalues and eigenvectors. So regarding the definition of eigenvector, a non-zero vector x is an eigenvector undernamed characteristic vector of a square matrix A if there exists a scalar such that Ax equal to lambda x, then this lambda is called the eigenvalue or characteristic value of A. That means if a vector which satisfies Ax equal to lambda x, where lambda is a scalar, then we can say that x is called the eigenvector and that lambda is called the eigenvalue of that matrix. That means, so Ax equal to lambda x, from this we get Ax minus lambda x equal to 0. So here we get A minus lambda I of x equal to 0. So the determinant of the matrix A minus lambda I, if it is equal to 0, then we get a characteristic, then we get an equation in lambda and it is called the characteristic equation of A, and the roots of this characteristic equation is the roots of this characteristic equation gives the eigenvalues of A. So the important points in this slide are eigenvector, eigenvalue, and then the characteristic equation. And note that the zero vector cannot be an eigenvector even though A into 0 equal to lambda 0, lambda equal to lambda into 0, but lambda equal to 0 can be an eigenvalue. And for example, in this example, we have to show that Ax equal to lambda x. Consider the vector 2, 1 and show that, and this vector 2, 1 is an eigenvector for the matrix A equal to 2 minus 4, 3 minus 6. First find Ax. We get Ax equal to the 0 vector 0, 0. And but for lambda equal to 0, we get lambda 0 into that x 2 1 equal to 0. Thus we get Ax equal to lambda x equal to 0. Here we can say that A is the x is the eigenvector of A, also lambda is an eigenvalue of A. And for discussing the more examples, find the eigenvectors of A. In this matrix, we are going to find lambda I minus A. Here, this is a 2 by 2 matrix. So, here the identity matrix is the 2 by 2 identity matrix. So, determinant of lambda I minus A will be determinant of lambda minus 2, 12, minus 1, lambda plus 5. Finding the determinant, we get the characteristic equation as lambda square plus 3 lambda plus 2 equal to 0. From this, we get two eigenvalues, minus 1 and minus 2. And the important point we have to notice is the roots of the characteristic equation can be repeated. For example, if lambda 1 equal to lambda 2 equal to etc. lambda k, if that happens, the eigenvalue is said to be of multiplicity k. Consider the example 2. In this example, after finding the characteristic polynomial, we get the characteristic equation as lambda minus 2 the whole cube equal to 0. Here, lambda minus 2 is a factor which repeats 3 times. So, we can say that lambda equal to 2 is an eigenvalue of multiplicity 3. Next, we are discussing about the properties of eigenvalues and eigenvectors. Before entering into the property, we'll discuss an important definition called trace of a matrix. Trace of a matrix is the sum of the elements on the main diagonal of a square matrix. I repeat, the trace of a matrix is the sum of the elements on the main diagonal of a matrix. And the regarding the properties of eigenvalues and eigenvectors, we can find the trace of a matrix using the sum of the eigenvalues of a matrix. So, first property regarding the eigenvalues is the sum of the eigenvalues of a matrix is equals to the trace of a matrix. And the second property, a matrix is singular if and only if it has a zero eigenvalue. And we all know that a singular matrix is a matrix with determinant equal to 0. Property 3. The eigenvalues of an upper triangular or a lower triangular matrix are the elements on the main diagonal. And about property 4, if lambda is an eigenvalue of A and if A is invertible, then 1 by lambda is an eigenvalue of lambda A inverse. Property 5, if lambda is an eigenvalue of A, then k lambda is an eigenvalue of the matrix Ka, where this k is an arbitrary scalar. Property 6, if lambda is an eigenvalue of A, then lambda raised to k is an eigenvalue of the matrix A raised to k for any positive integer k. Property 8, if lambda is an eigenvalue of A, then lambda is an eigenvalue of A transpose. That means the eigenvalues for a matrix and its transpose are same. And the last property, the product of the eigenvalue of a matrix gives the determinant of the matrix. Thank you.